All right, get it full screen. So the last problem on lesson set 26 through 29, maybe 30, it's been about kind of a little entry level question, getting us a discussion started on some early calculus principles. Don't let the word calculus scare you. It's all about algebra 1 at this stage. I mean, that's all I'm going to use is algebra 1 to present this topic in what I hope is a meaningful way and a way that you can start to look at the numbers at work, mostly a numerical perspective in this particular video. The sooner you start talking about some of the higher level concepts in math, I think the better chance you have of success in future classes. So I'd like you to be exposed to some of these concepts. And I hope it helps you when you finally get into a more formal study situation. All right, so let's have at it. So finding the vertex of a quadratic via using calculus. Okay, that's what we are doing with the last problem in that series of lesson sets. So here's the numerics. All right, I've got a handout for the class, and it's got these table values in it, in that handout. But you can pause the video, and I would suggest you spend 30 or 45 seconds looking at squaring. 0 squared is 0. Squaring 0.001 gets us 0.000001. Okay, and I'm not using a calculator. I haven't checked those values in 10 years. But I know that 3.0001 squared is going to get me 9.00060001. This time I used even a smaller change in x. All right, so what am I doing there? I'm really looking at the slope between 2 points. I'm looking at the change. All right, and this is a pretty small change in x. And if I doubled it, if I doubled x squared, then I get double the change. All right, so take a moment, spend some time here. Your future classes depend upon your understanding. This is the entry-level problem. This is what I believe Sir Isaac Newton looked at. And we're going to look at it geometrically in a moment as well. But the numbers are saying something. So look at the rates of change. Divide the change in x by the change in y and approximate what that change is. And if you do, I think you'll see that when x is 1, you're changing by 2. When x is 2, you're changing by 4. When x is 3, changing by 0.0006 divided by 0.0001, changing at 6 to 1. I think there's a pattern there. Okay, so where's the pattern coming from? Well, let's move along. Okay, so we've got 0 squared is 0, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. Yeah. And if we take this 3 times 3 and look at it from a geometric standpoint, well, 3 times 3 is 9, but I'm increasing the side length by 0.0001, and it's giving me some new area that I don't know how to show you because visually a change of 0.0001 kind of hard to show. It's kind of like a new layer of area. Okay, and even that's probably too thick, right? That's probably more than 0.0001 units of change in this drawing. But to show 0.001 times 3 gets me in the upper quadrant, upper section of this drawing, 0.000, I don't forget how many I said, 3, and 3 more. Well, there's our 6 to 1 ratio that was really being shown in the table over there. And 0.0001, whatever, 3 zeros and a 1 squared gets me 8 decimal places with a 1. I don't think that's significant with respect to these numbers. It's not changing this much. All right, so in an underhanded way, I'm sneaking in the concept of a limit right now. All right, making the brain process that a little bit. And the change in y, and I'm going to use dy to represent y2 minus y1. Okay, so this is the change, and that's the change, right? And so that adds up to, well, remember, we're looking at functions in terms of x. So what's happening? Well, this is just a generic square, and so that's an x and that's an x. There's your x times x, your side lengths. And it sure seems like the rate of change is connected to that length. Seems like the bigger that length, the bigger the change from, say, when it was 2 to 2.001, things were changing at 4 to 1. When it's 3, it's 6 to 1. Seems like it's linked to the length of the side of the square. That's how the rate of change is changing. Didn't want to say that. That's how the area is changing. Okay, that's how the position or the amount, the initial amount, 3 by 3, 9 units of area, 3.001 squared, 9.006, 001. I don't care how many zeros you give me 50 zeros, and it's 9.00601. Oh, yep, should have gone to the Juilliard. All right. So how do we use that knowledge to graph a quadratic? All right, well, I think we can come up with the formula for change. If y equals 2x squared plus 12x minus 7, when I doubled over there, the rate changed by a factor of 2. And what was the rate of x squared? Again, nobody's asking you to learn this immediately. It took hundreds of thousands of years for this to evolve intellectually. All right, and dx, I mean, if I'm calling a change in the area dy, I think I can call the change in x dx, difference in x's, dimensional change in x. It's hard to know how it was initially described in terms of what the folks who were creating this said at the time. I think I can think of it as a dimensional change or small change in whatever x value I'm working with. All right, and if you factor a little algebra, if I'm multiplying this term by that little change and that amount by that little change, I haven't spoken about that change, but if you look at a linear function, you take 12 times 1, you get 12. You multiply 12 times 0.001, you get 0.012. It's going up at 12 to 1. Linear functions change at a constant rate, over, up, over, up, over, up. All right, so this is basically dividing dx to the other side. Dy dx, you can think of dy dx as y2 minus y1 over x2 minus x1. And in this case, we get 4x plus 12 in this particular case. And then if I take, and I can write instead of dy dx, in calculus, we often say just y prime. And it's quicker to do that, to write that. So it makes sense. Y prime. This is telling us the rates of change of this quadratic. And if I take the rate of change of the rate of change, I get the number 4. Okay. So eventually you work with position statements, velocity statements, and acceleration. That's kind of one of our first forays into physics. We use math to study things out in the real world, physical things out in the real world, the way things move and change. Okay, so what's 4 as an acceleration? Well, we'll go back to x squared. X squared at 0 changes at 0. It's not changing. At 1, it's going up 2 to 1. At 2, it's going up at 4 to 1. At 3, it's 6 to 1. Well, it seems to me that the rate of change continues to go up by 2 each time. And if I'm doubling that rate of change, 4 tells me that things are accelerating. And that's the right-hand side of a quadratic. It's accelerating in terms of the numbers. Then you give me a little change, and then you give me a number that's bigger than the one you started with. The next change is going to be bigger. Okay, so if we look at, I got to change René Descartes over to this board. So excuse me, a little housekeeping here. Move this chair. All right. Let me bring this closer. All right, so we got this board. So a repeat of what I wrote over there. All right, and here's a repeat of the conversation we just had. I forgot I'd already written this. I should have turned the camera over here sooner. So if a is greater than 0, right, positive x squared, second derivative was positive, so we got a concave up shape. And 4x plus 12 is telling us how this function is changing at any instant. Right? That's its rate of change. So what's the rate of change at a vertex? Well, we use tangent lines to indicate change at an instant. Okay, so what's the slope there? Sure looks like the slope here is 0. Well, when does 4x plus 12 equal 0? Sure looks like -3. So we basically are finding that value. And we get a sense of, that acceleration, right? And so we could plug in different numbers, and I'll plug in 0 this time, just to see what I get. So the rate of change at 0 is 12. Oh, geez, I think we've been looking at problems like this and how we've been doing them in class at the algebraic level. The algebraic level, I look at that. Let's get rid of this. Okay, let's get rid of this because we just talked about it. So how did we do this? Well, we said, oh, we know we have that shape, right? We've done enough of them to know that shape. We did minus b over 2a, I almost said 3 because we're starting to work with the cubic. So that's minus 12 over 4, 2 times 2. Oh, -3, what a coincidence. What a coincidence. And if you put -3 in, you get -36 -36 cut in half, -18, -7, -25. That should sound familiar. And what should also sound familiar is that I said at the y-intercept, you're going up at 12 to 1. Okay, well, here's justification that you're going up at 12 to 1 right here at -7. What's the justification? Well, we've been doing this for the last month, been trying to show you how things change if you change by, some small amount. It gives you a feel for a change at an instant. And by God, look at that. The major change certainly isn't occurring there. Constants don't change. There's very little change coming from the quadratic at 0. The majority of numerical change is coming from the linear term, 0.012. And if you divide by 0.001, you get 12 to 1. Oh my, what another coincidence. Such a nice coincidence. All right, so just a little bit more of a chat here. Coming back over here. Almost done. The pain is almost over. So I just have another problem. We'll do it together and we'll attach it to a physical context, and then we'll know why we study mathematics. So x squared changes by, remember, the two sides of the square, that layering process, 2x, and linear changes change by the coefficient. 5 is not changing. If you see it change, we talked about that in the past. Give a call, write it in the comments, give me a contact number, and we'll get you some help. All right, so I just drew. This is my art skills. Right, very good. I've lived in this area my entire life for the most part. A little more travel these days, but I've either been in Providence, Rhode Island. I didn't do a good job with Rhode Island. Sorry, Rhode Island, you're down here somewhere. All right, so Providence right about there. Well, we're here. 91 goes north-south and goes through Vermont, Massachusetts, and Connecticut, so on and so forth. So let's pretend that this is Grandma's position. She's out on Route 91. All right, in a car, I guess, probably on Route 91. All right, and so that's going to tell us like her position. Let's just pretend. I give you a number, time of the day, like 0. So at 0, Grandma's 5 miles north of the Vermont, Massachusetts border. She could be heading north or south. Our velocity is going to tell us that positive number, positive, she's heading north, negative, she's heading south. Okay, and double prime will tell us if she's accelerating, and it seems like she has constant acceleration. Okay. Not quite sure what grandma's doing, but that's why we're doing the math, just in case, grandma needs some assistance. And so 3 hours ago, let's think of that as hours in the day. 3 hours ago, grandma was at -18, -9 plus 5, -4. So she's 4 miles south of the border. And what's she doing? -3, she's stuck. Oh yeah, if I drop in a -3 here, we get a 0. And the 0 is, well, yep. On her journey, she's stopped. Okay, right now, what's she doing? Well, that's 3 hours in the future from 3 hours in the past. Well, if I put in a 0, she's going 6 miles an hour north and she's 5 miles above the border. So she's moved position. She's now 5 miles above the border and she's going at 6 miles per hour. Well, I don't know about you. I mean, I'm getting old too. I mean, this could be me driving there. All right. And, I'm hoping that if I'm stopped 3 hours ago and I'm walking north at 6 miles an hour, yeah, I could be on foot. That's not a good thing for grandma out on Route 91. Cars are going pretty fast. So, if anybody ever asks you why you study math, I hope you tell them I might need to save grandma, I might need to help her out, or me. I'm getting there. Okay, so and I want you, no pride here. If I'm doing that, come get me, help me out. It could be somebody else, who knows, but that's why we're studying math. Now, I have forgotten to do this. I said I was going to do this. All right, I was going to come over here. I've got a 2x2, which is 4 units of area. And I said, I'm going to add a little layer every time. And I'm going to do it until I get to a 3x3 square, which is here. I'll do that. I'm going to fill that in with a layer every single time. I don't want you to think about what I'm doing, because we're going to describe that process symbolically over the next 7.5 weeks. No track meet here. There's no reason to sprint through this. I'm just going to talk about it 30 seconds a day. It's not going to hurt anybody to talk about this for 30 seconds a day. So the next video, I hope I remember to come over here and draw another. I'll do it right now. Another area of another example of, well, I don't want to say anything. I want you just to interpret that yourself. And then we'll talk about it. We'll talk about it a little bit each day. That's enough for today. Okay, we're done. Still fairly cold here, so stay safe and warm. Toodaloo.